Okay, we have a 60 Newton disco ball. It's hanging above. I'm going to go through this question really quickly. We're using static equilibrium equations because this disco ball is not moving. So to recap, we have BA, BC, BD as three strings holding this ball in tension. What is most nearly the force in cable BD for the disco ball to remain in static equilibrium so that the wire does not collapse? So we're looking for cable BD force. You can find all of the forces in the cables. Um, we're given some of the unit vectors, but we can find them from scratch real quick. So the unit vector equation, we'll put it up here. So unit vector U is position, like the position vector, and divided by the magnitude of the position vector. And you can think of it as like the force as a vector. You have, let's say, force BD. That's what we're looking for, times the unit vector. So this is the uh, force as a vector, and you have the magnitude FBD, and it's times by the unit vector. So to do this, we're going to get the unit vector for all of the cables, FBD, BC, and BA. I'm going to put it in um, static equilibrium. So sum of forces in the x direction equals 0. Sum of forces in the y direction equals 0. And then that should be sum of forces in the z direction equals 0. We're going to take the cable position vectors. So let's look at FVA. That's this cable. I'm doing FBA times U, and that will be U as a position um, from the coordinate system. I'm doing a x coordinate part. So that means in the x axes, there is no x component, it's 0. And the y, there is a -6 because it's going back from point B to A. So we have a 6-meter distance. And then for the Z, we have a 12-meter distance. And we're dividing each one by the magnitude. The magnitude is, we're going to call this magnitude of U, is the square root of 0 squared plus -6 squared plus 12 squared. That gives us 13. So everything is going to be divided by 13. And that's our first vector. We do that for the rest of them. F, B, C, U. F, B, C is -4, 8, and 0. Looking at from B to C, the distance in the X, like from point B to point C, there's a 4-meter distance, and it's in the negative part of the X axis. There is 8 in the Y. From B to C, there's a gap of 8, and it's from B to C, so it's +8, and then there's a 0 for Z axes. And if you do the magnitude of -4 squared plus 8 squared plus 0 squared, it's 8.9. And then lastly, FBD. Go through that whole process. You end up with FBD 0.447, 0.894, and 0. Simplifying the other ones, negative 0.447, 0.894, and 0. Okay, the next part is to do things in static equilibrium. So let's start with the z. In the z-axis, there's only this force in the cable pointing up in the z-axis, and then there's a weight going down. Let's do that. You can also do this with triangles where you have this tension BA projected to the z-axis. In my case, we're just going to do the actual components like looking at um, these parts here. Then I'll simplify this top one too. FBA 0, negative 0.447, 0.894. Okay, so to highlight that, we have that, that, and that. So let's do sum of forces in the z-axis. We got 0.894 FBA. That's from this top one here. Then we have plus 0 FBC. Sorry, forgot the C there. And then plus 0 FBD. And we have a minus of this weight. The weight is 60 newtons, according to the problem, equals 0. So we have 0.894 FBA equals 60. FBA equals 67.08 newtons. So we have FBA solved. Then let's do the other static equilibrium equations. Let's do sum of forces in the x direction. So we'll take those components again. So FBA here in x is 0. FBC, negative 0.447 FBC plus 0.447 FBD equals 0. Then we have sum of forces in the y direction. I'm taking that last component, 0.894 FBC right here. Oh, there's also an FBA, negative 0.447. And then a 0 times FB, oh, sorry, 8.94, 0.894 FBD. All of that equals 0. And we said earlier FBA is up here, so we can substitute that into here. So solving all of those, it's a system of two equations and two unknowns. So you can substitute things. So these two, solve those, and you'll end up getting FBA. I'm rewriting this part. FBC 16.4 newtons and FBD equals 16.4 newtons. So these are your answers here. And let's look at the question again. So we have 16 newtons in this disco ball, we don't know any of these tensions. We were able to do the equilibrium equations and solve with a system of two equations and two unknowns. Another way to do this, same method, instead of using the unit vectors, you can use triangles. So in the, let's say the equilibrium equation with f of x equals 0, you look at all of the forces along the x-axis. So we have this force BC, BD. There's no force along the x-axis because of this AB projected downward. There's no x component. So you can add up the forces in the traditional way using triangles. Um, Here's one more. F of y equals 0. You look at it in the y-axis. So we have y component of this force, FBD, y component of FBC. There's a y component of FBA. There's no y component of the ball going down. So you add up those, solve for the unknowns. And then another last thing is that these forces are symmetrical, FBC and FBD. They are set up that they're both 4 meters away from the center line. They're both 8 meters back. So they look symmetrical. The measurements are symmetrical. That means the forces are kind of equivalent. So force in FBD is the same as force in FBC. If it is not symmetrical, you can't really make that assumption. Or if there's forces that are external and it kind of is not symmetrical with the system. So whenever it's not symmetrical, you can always fall back on this style of equilibrium equations and solving them. So there you go.